Okay, so this is going to be a short video to just recap some of your chemistry that you might have had at school or from Evolution of the Living Earth course. To go over some of the things that you're going to need to know for the gases and climate lecture. So in the lecture we're going to be talking about CO2 and oxygen and how those behave in the ocean and why they're important. So to do that we're going to need some recaps of some of the chemistry that you will of course done before, but this is just to make sure that you've got the necessary background. Okay, so the first thing is to do with the concentrations of dissolved gases in a liquid. In this case we're going to be interested in water, and how those relate to the concentration or the amount of those gases in the gas above that liquid, so usually the atmosphere in the case of what we're going to be talking about. So the thing to remember here is this concept called Henry's law, which named after some guy called Henry who presumably came up with it, is that the concentration of gas in a liquid is proportional to the concentration of the gas in the kind of gas above it. So that relates basically how much the solubility of the gas, what the concentration in maybe grams of gas per kilo of water, and is related to this thing called the overlying partial pressure. So this is the pressure of the gas times the proportion of that gas, which is the gas we're interested in. So if we're looking at, say, the atmosphere, it would be, and CO2, it would be 1 atmosphere of pressure times the proportion of the atmosphere which is made up of CO2. So this relationship between the pressure of the gas and the concentration in the solution is related by this solubility constant. So if we just increase the concentration in the gas above, okay, the concentration that is dissolved in the water will correspondingly increase. Now, unfortunately, this terminology of a solubility constant is a little bit unfortunate, because the solubility constant is not, of course, a constant. So it varies with environmental conditions, and we'll see it varies with salinity, but most importantly I think it varies with temperature. So you can see here that as temperature increases, the amount of gas that we can dissolve in any liquid, proportional to its concentration in the atmosphere above, decreases dramatically with temperature. So at very cold temperatures we can maybe dissolve quite a lot of gas in a liquid, but at warmer temperatures less of the gas dissolves in the liquid. And different gases have slightly different relationships, but you tend to always get this relationship. The colder something is, the more gas you can dissolve in the solution. Okay, so that's something to think about. The next thing that we're going to be using in the lecture is pH. So pH is a measure, or is a way of expressing the acidity of a solution, or how basic that solution is. So I'm not using the term acid and alkaline, because you'll see in the lecture that actually alkalinity is something different from how basic a solution is. So just for pH, so this is looking at the acidity or basicness of a solution. So this is referring to how much what the activity of hydrogen ions are in that solution. The activity is of hydrogen ions in solution. Actually, when looking at pH or acidity in solutions like seawater, because the ionic strength is so high, it actually is a little bit more complicated. But for the purposes of our lectures, we're just going to be concerned with the activity of hydrogen ions, and actually we're going to ignore the term activity and just assume that activity and the concentration of hydrogen ions are the same. So pH, if we use this slightly different formation or kind of approximation of pH in solution, so the pH is related to the concentration of hydrogen ions in solution by this kind of log minus log 10. Okay, and what this means is that we can express a huge range of concentrations over many orders of magnitude. So up from maybe tens of moles per liter down to kind of micro and milli and nano and picomoles per liter of hydrogen ions in solution. Okay, so the way this expression here kind of like works is that you take the concentration of hydrogen ions, so for example 10 moles per liter, so this would be a very strong acid, with kind of like maybe concentrated hydrochloric acid, about 10 molar. We take log to the base 10 of 10, which is 1, and minus that gives us minus 1. So the pH of 10 molar HCl should be around -1. Whereas solutions with much lower concentrations, okay, so if we look at, for instance, this is an example of maybe pure water. Okay, so we'll have a concentration of hydrogen ions of maybe 0.0000001 moles per litre of hydrogen ions. So that can be expressed as pH. So we take that 0.0000000 whatever it is, log to the base 10 of that. That gives us -7, and then we minus that, and that gives us a pH of 7. Okay, so that's how we can kind of use this term pH to represent large variations in the concentrations of hydrogen ions in solution. Okay, so just bear in mind that that's really all pH is when we're using it. It's just the concentration of hydrogen ions in solution, and when the pH is a big number, the concentration is very small, and when it's a small number, the concentration is higher. Okay. So moving on now to chemical equilibria. So we're going to be looking at two types of chemical reactions in the lecture. We're going to be looking at unidirectional reactions, which basically take reactants. They react together to form some products, and those products then stay as products. They don't then back react to form the reactants again. Okay, so an example here is respiration. Okay, we take organic carbon and oxygen, and we breathe that, or we burn it, and we produce CO2 and water, and that CO2 and water don't spontaneously combine back together to form the organic carbon and oxygen. I mean, there is a separate process of photosynthesis that does that, but it's not this reaction of respiration. They're separate reactions. Stop. Okay, so the other kind of reaction is a equilibrium reaction. Okay, this is where we have a set of reactants that might react together to form a product, but rather than that product being kind of either stable or basically kind of going away or not interacting anymore, our product can basically react back and form the reactants again. So there's this constant exchange between reactants and products going backwards and forwards. Now the relative proportions of those two, it's not going to necessarily have 50% of one, 50% of the other. You can be very, very biased towards one side or the other. So you could only have a small amount of reactants because the equilibrium point is much further over towards the other side of the reaction. And importantly, we can change the relative proportions of these things by changing environmental conditions. Okay, we can also change the relative proportions by adding more or less of the products or reactants, and basically shifting our equilibrium to one side or the other. So in this case, we've got CO2 reacting with water. That forms this compound here called carbonic acid. Okay, then that spontaneously can break apart again into CO2 and water, and actually in this case we hardly have any of this in solution at all. Okay, it mostly favours CO2 and water. Okay, but it doesn't just stop there. In the case of what we're going to be looking at in the lecture, that the carbonic acid can spontaneously break apart into rather breaking apart into CO2 and water, it can dissociate into bicarbonate ion and a hydrogen ion, and then once again that can break apart further and form the carbonate ion and another hydrogen ion. So we have this series of equilibria, okay, backwards and these carbon species will be constantly changing between one form and another. But at any kind of one point in this, there will be different proportions of CO2, of carbonic acid, of carbonate ion, and of bicarbonate and carbonate ion. Now the relative proportions of those depend on the positions of each of the equilibrium reactions. Okay, and importantly, we can change those relative proportions by adding or taking away these hydrogen ions. So the more hydrogen ions we put in, the lower the pH, the more this back reaction kind of goes. So we're basically adding in hydrogen ions. That forces the reaction towards this way. Adding a hydrogen ion here, it will force the reaction this way. So in this case, the pH is determining, or is a strong determinant of the relative proportions of our products and reactants in these equilibrium reactions. Okay, so hopefully this little recap has been useful to you. So you should know about what determines the gas concentration in a liquid. You should know what pH is a representation of, and you should hopefully know the difference between a one-way reaction and an equilibrium reaction that goes backwards and forwards. Okay, so now hopefully now you should be looking forward to using some of these in the lecture. Okay.